For this lesson, we're going to wrap up our look at exponential functions by taking a look at the applications of exponential functions. Exponential functions are actually very useful for modeling a number of real-world relationships. Many of the processes in the natural world, biology, chemistry, and physics, can be modeled this way. There are some elements of economics that can be modeled this way, and many others, So in general, when we talk about the applications of exponential functions, we're talking about two broad categories. One of those is exponential growth, which you can see here on the left, and one of those is exponential decay, which you can see here on the right. And the idea is as simple as those words make it sound. In exponential growth, if we proceed from left to right, if we're reading our graph from left to right, in the case of exponential growth, then the graph is always going to be increasing. If we have exponential decay, then as we read from left to right, then the graph or the data is always going to be decreasing. In terms of the equation, we talk about the base of the exponential function. So that's this value b. And in the case of exponential growth, that b value is always going to be, first of all, no matter what in these exponential equations, the b value is going to be positive. In the case of exponential growth, that b value will be a positive number that's greater than 1. And in the case of exponential decay, we're going to have a b value that is between 0 and 1. Still positive, but between 0 and 1. Now, as far as the other numbers, or this is a very simple equation, I had to make this other equation slightly more complicated simply because I wanted you to see kind of a symmetry there, but that wasn't necessary. So long as this base is greater than 1, you're going to have some sort of increasing. So long as this base is between 0 and 1, you will have some sort of decreasing exponential decay. Now, when we look at the equations for applications for growth and decay, you can generally break those equations down in their simplest form to having only the parts that I'm showing here. In terms of transformations, which is something that we look at a lot in this course, in terms of transformations, we really only concern ourselves with the vertical transformations. Now, that's not to say that you can't have horizontal transformations, or that's not to say that when you think about or look at graphs or relations, you might still think in terms of horizontal, and that's fine. But you can always break these things down to vertical transformations only, and that can be quite helpful. So that's just something to keep in mind, and as we work through some examples, I hope that that will start to make more sense to you. When we talk about growth and decay, another way that you'll hear these mentioned is in terms of a growth rate or a decay rate or a rate of change, something along those lines. So in general, if we called R that rate, then we can come up with our expression for the base of the exponential function very generally in terms of either 1 plus that rate if it's growth, or 1 minus that rate if it's decay. So if we have a situation where we say, for example, if we had a situation where we said that the population is growing by 10% per year. So 10% per year would go here. That would be the R. So we would have an R value of 10%. And normally we don't use percentage signs once we're actually doing the math. Percentage signs are useful for summarizing or for describing things, but we would normally write that rate as 0.10. And so the 1 here represents the 100% that was already there, and then what we're adding is 10%, or we're adding 0.1. If we are, let's say, losing 10% per year, then the way we describe that is our rate is still 0.10, but in this case we would take the base would be equal to 1 minus 0.10, which would work out to be 0.90, and the literal interpretation of that, 0.90, we know we could also state that as being the same as 90%. So what this one would be saying is if we lose 90% of the population, let's say, in a year, then that would mean that, I don't know if I said 10 or 90. If we lose 10% of some amount per year, then that would mean that 90% is what's left over. So I want you to see why we write that or why we talk about it that way, and that it is consistent. Now, the other thing that we talk about when we're talking about exponential equations, particularly when we're talking about the graphs, is we're quite often interested in the horizontal asymptote. And that comes from this Q value. So whatever the Q value is, that's basically telling us that there is a horizontal asymptote at y equals Q. So when we are doing these applications, the horizontal asymptote could be any number of values, and you do have to be very careful and think about that. But most often, the most common application of an exponential function is probably going to have a horizontal asymptote at 0. And that just means that in a lot of these situations, 0 is the practical lower limit for these values that we're looking at. Whether that is a 0 population, you can't have less than, you can't even have 0 as a population. At least not if you're going to model it using an exponential equation. You talk about the value of things. There are a number of them that fall into this category. So again, something to keep in mind. And finally, I know I'm setting up a bunch of things here. Oh no, I'm going to go straight on to an example. Okay, that's good. I thought I was going to go on to the next kind of theoretical section. But let's do an example now. So in the town of Wood Buffalo, Alberta, they saw a large population growth over recent years. Now that probably isn't actually still true, but through the mid-90s into the 2000s and well into the mid-2010s up to 2015, there was oil found there, and a lot of industry grew up in that area of Alberta and surrounding areas. And so they saw a lot of growth. 8% is a lot of growth in terms of population, particularly in terms of human population. So we can model this using an exponential function or an exponential equation. Now this is worth mentioning here. These models, whenever we model any situation using an equation, the model is only valid for certain periods of time or over certain parts of the domain. It's not going to always be true. And so in this case, we're going to assume that this model is valid from 1996 until present day. So the initial population was 35,000. It's been growing by around 8% per year. What is the approximate current population? So for questions like this, probably the first thing you're going to want to do, well actually since we just talked about it, let's take a look at this, 8% per year. Well, that is our rate. So our rate is 8%, which we are going to express as 0.08. Since this is population growth, we can now write the base of our exponential function is 1 plus the rate, which is 1.08. The 1 represents the 100%, the people who were there from the beginning, and the 0.8 is going to say, and each year we're going to add 8% to that population. If we use that simple exponential equation, the simplest one that we can come up with, ab to the x plus q, well, we already have our b value, so that's good. We've got one thing covered. Now let's talk about that idea of the horizontal asymptote. If I were to draw, or just a very quick sketch of what the population might look like over time, and in this right here, well, we have to define this at t equals 0. I'm going to say that that is 1996. There is a way for me to do this where I actually use the actual year in here, but it makes things more complicated. Whereas if I just do this very simple let statement, let t equals 0 represent 1996, I save myself a whole lot of trouble. So if I do that, when t is equal to 0, what's the population? when t is equal to 0, which means 1996, the population is 35,000. So I'm going to go ahead and put that as my y-intercept. So this is the population as a function of time. And so we know that the population from here is exponential growth. It's going to go up and up and up in that classic exponential growth curve. Now, I mentioned that this model, we only know that this model works from t equals 0 to t equals, well, modern day, present day. But if we imagined time flowing backwards, and if the model were still applicable, then this curve would continue to decrease, decrease, decrease going backward, but eventually it would get to an asymptote. And so the question I'm asking is, where would that asymptote be? Well, could we have a population of the town that once upon a time was half this much? Sure. What about half that again, or half again? Technically, we could keep going backward and backward and backward until eventually, in theory, we could get back to a population that was close to 0. And it turns out, for the purposes of these equations, even though we can't have a decimal, a portion, or a part of a person, we actually make that assumption. So we are going to make the assumption here that the horizontal asymptote occurs at, well, in this case it would be at p equals 0, because that's a population of 0. And so that we're going to artificially set the value of q equal to 0. When you're dealing with populations, usually you're going to have a q value of 0. So that immediately simplifies our equation further. So now we end up with an equation of y equals a, but instead of b, it's going to be 1.08 to the x. And actually, I should, let me just, you know what, I'll leave it that way for now. But now let's start to put it into a form that's a little bit more meaningful, which is the population as a function of time is equal to a 1.08 to the t. And let's make use of, once you become comfortable with this, you won't need to go through this much trouble. But we know that at t equals 0, right? So t equals 0 is right here. At t equals 0, the population is equal to 35,000. And so from there, we can actually say, okay, in that case, 35,000 is equal to a times 1.08 to the 0. Well, that occurred when t equals 0. But we know from exponent laws that anything to the 0 is simply equal to 1. So that means that 35,000 is equal to a. And so now we have our equation. Now you don't normally need to go through this much trouble. The population as a function of time is equal to 35,000 times 1.08 to the t. So you don't normally need to go through that much trouble to come up with the equation, but once you get more comfortable with it, you'll be able to go directly or almost directly to that equation. Now, what is the approximate current population? So in this case, right now, we're just going to, very coarsely, we're just going to say that the year is 2020. So for now, the year being 2020, but t equals 0 is 1996. So t is going to actually be 2020 minus 1996, and that's going to work out to be 24 years. So 24 years have passed since this growth streak started with this town. And so to finish up the question, we want to know what is P of 24. And that's equal to 35,000, 1.08 to the power of 24. And I've got a calculator handy here. So first thing I do is the 1.08 to the 24. And then I multiply that by the 35,000. And I end up with a really a ridiculously large figure. I'm sure it didn't sustain this population growth for this long, but you never know. 221,941. 221,941. And we should finish this with a therefore statement to wrap that up nicely. I'm not going to do that because writing with this tablet is bad enough at the best of times. So that's it for that particular question. So that's an example of an exponential growth where we had to figure out what the new base of the exponential equation was, and we had to think about a couple of other things as well. Now, there are sometimes when we deal with exponential growth and decay, there are certain situations that come up so frequently that we've given them their own equations. But I need you to understand that these are still just exponential growth and decay. They're just dressed up a little differently, and we've brought back in the horizontal transformations that we took out before. So these are optional forms, but they are actually very convenient to work from. The first one is the doubling period, or the doubling equation. It makes use of the idea of doubling period. That's the concept. In a lot of situations, it's easiest to think about, particularly when you have something that's growing very rapidly, it's easiest to think about, well, how long did it take for it to double? So instead of sticking with this simple equation that only makes use of vertical transformations, we modify the equation where the x value, the exponent, we actually express it, and you can see it even in the doubling period equation has t over d. It's almost always going to be talking about some kind of time for the doubling period. And so we replace the x with a t over d. Now, replacing that x with a t over d, we've introduced one of our horizontal transformations. And you can choose to think of it that way or not. Okay? I'm going to show you how these things are equivalent to each other. I'm not going to show this video. I would normally show this in class. This is just a bacterial cell division and just showing what that doubling can do, how quickly it can occur. But being mindful of time, let's move on. The other thing I want to talk about is something known as half-life. In terms of applications of exponential growth and exponential decay, this is the one that most students are immediately familiar with because you've heard this, probably this term half-life. You may have heard it in correct scientific terms, or you may have heard it used in some sort of colloquial setting in society, may or may not have been used correctly, but it is probably a familiar term to you. And this is just an exponential decay equation. Very similarly, the exponent x, instead of keeping it in this simple form, we take the exponent x and we put it into this slightly more complicated form. Once again, the numerator is t. This is almost always going to be referring to times. And the h value in this case is the half-life. That's the amount of time it takes for the substance, whatever it is, the amount, the mass, the population of the substance to go to half of its original, and then half again, and half again, and half again. So we end up with this slightly modified equation. So let's take a look at a couple of examples of that. We have a certain bacteria doubling every 4 hours. Okay, so first of all, doubling every 4 hours. That tells us that the doubling period is 4 hours. Right away, we can identify that. The initial population is 36. Now, and we would normally write that as what's known as P0. The naught means initial, so that would be an initial population of 36. But that initial population is going to also match up with our A value. And since it's a population, the lowest population that we can have that's possible is 0. And so we set our Q value equal to 0. And that's going to make our equation much simpler. In terms of a population, I'm going to write this now as a population as a function of time is equal to, and in general we would write this, P0, it's a doubling period question, so it's 2 to the exponent t over d, and I've already set my Q equal to 0. So P0, the initial population, is 36. 2 to the, and the exponent is going to be t over 4. Now, if you write it this way, because we don't normally include our units, then you must keep in mind that the units, the only units that currently work for this equation are hours, because that is the d value. So whatever value I put in there for t, I also have to use hours. Now, that's okay, because you can see in part B, I'm given a time in hours. So all I need to do here is say, what is the population after 8 hours? And that's equal to 36 2 to the 8 over 4. And so that works out to be, now I've chosen numbers that are really very nice here. 2 to the 8 over 4 is the same as 2 to the 2. And so that ends up being 36 times 4, which is 144. So therefore, the population after 8 hours is 144. We could, however, have simply used the regular, if you want to call it that, the more general exponential function to do this. We could have done the exact same thing. And things are going to work out very similarly. In this case, I'm still going to set q equal to 0, because that hasn't changed. But now I have to do a little bit more work, because what I have to do now is say, okay, I'm going to rewrite this in terms of a population. So population as a function of time is equal to an initial population, which was 36. But now I don't have a value for b, and instead of x, I'm going to put a t there. So if I want to do this type of model, now I have to figure out, what do I use for my b value? And so what I do here is we know that p at 0, actually, is that going to work? No, we won't be able to use this. Sorry, that relationship won't help us here. The p of 0 relationship helps us find that a was equal to 36. But what do we know? We can make use of the fact that p at 4, so after 4 hours, it doubles every 4 hours. So after 4 hours, what's the new population? It has doubled, so it's double 36, which is equal to 72. And so now I can use that relationship to find my value for b. So now I get 72 is equal to 36b to the 4. Divide both sides by 36 to simplify things. So divide by 36, divide by 36, and I end up with 2 equals b to the power 4. Now, how do I get rid of the power 4 part? Well, technically, the opposite, just in the same way that the opposite of squaring is square rooting, the opposite of to the power 4 would be the 4th root of 2. We don't need to say plus or minus here, because the b values are always positive. So we're going to reject the plus minus because we know the b values are positive. It's actually, from your calculator, it's probably more convenient. Instead of doing the 4th root, you might do 2 to the power 1/4. They both get you the same thing. And so that gives us a b value of, now this is the downside to doing it this way, is we start to get into approximations. So even if I keep quite a few decimal places, so 2 to the 1/4 is 1.1892, but that's going to be approximate, 1.1892. And then determine, so that means my model, p of t, is equal to 36, 1.1892 to the t. And so to find out the number of bacteria after 8 hours, I get p of 8 equals 36, 1.1892 to the exponent 8. And I'm going to use that rounded value. So 1.1892 to the power of 8 equals times 36. And I end up with 143.993. Now, is that a good enough answer? That's almost 144. It's pretty close. It's off by a little bit. Okay? And so that's because we introduced that rounding. And that could work either way. It just depends on how you're working through this. So we could do that same thing with exponential decay, for example. So I think I'm going to finish things up with a slightly differently worded or set up example. We've got a tennis ball dropped from 10 meters high. After each bounce, its height is 45% of the previous height. And that's another way of saying that it's losing 55%. So another way we could have said this is it loses 55% for each bounce. And you could see a question worded either of those two ways. So if we came down here, if we just draw the ground and we drop the tennis ball, then it falls 10 meters, and then the next bounce up, it only goes 45% as high as it started, and then it falls again. And the next bounce up, it only goes 45% as high, and it keeps... Now, this is the problem with mathematical models. In the mathematical model, it just keeps bouncing forever. But we know that that's actually not realistic. We know that eventually that ball is going to settle to the ground. And if we assume that the ground is at a height of 0, once again, we can justify having our Q value there at 0. Now I'm getting a little ahead of myself. After no bounces have taken place, okay, so if it hasn't bounced at all, well, then its height is 10. That's where it started. After one bounce has taken place, then its height is going to be 45% of 10, which is actually 4.5 meters. And now we have to get into the calculator, because after 2 bounces, the height is going to be 45% of the previous height, which is 4.5. So I actually have to take 4.5 times 0.45, which is the 45%, and I end up with 2.025. And then multiply that by 0.45 again. I end up with 0.91. And then multiply that by 0.45. I'm keeping these values in my calculator as I go, by the way. I'm not using the rounded values for my calculations. 0.41 and times 0.45, 0.18. And finally times 0.45, 0.083, so 0.08. I can't even graph to this level of precision, so that's far more than I actually need. I've got 6 bounces here. We're starting at 0, so I think if I do every 2, there's bounce 1, 2, 3, 4, 5, and 6. Now, obviously, when the bounces themselves occur, the height is 0. What we're interested in is what is the height that it bounces to? What's the maximum height it gets to? And we're starting here with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we start, let's switch to a different color. We start up here at 10. And then after the first bounce, we're at 4.5. And after the next bounce, we're at 2. And then we are at 0.4. You can see that's, 0.9. So that's about there. And then we're at about 0.4. And then we're at 0.2-ish. And then we're less than 0.1. And there's really no point. I'm going to have a very difficult time with the tablet trying to draw this. I might have to give up on drawing this. This is just trying to use the tablet to do this may exceed my coordination by a large amount. Give it one more try. Okay, well, that'll have to do, as terrible as it is. Clean these parts up. Okay, so there is our approximate exponential decay curve. And then the question asks us to, that's part A, create a table of values and graph. determine an equation that models the max height after n, so the variable is going to be n, bounces. Now we already decided that q was equal to 0. I just want to remind you of that. So what we're going to do is the height, or the maximum height as a function of the number of bounces n, is going to be a b to the n plus q. But of course, as I said, this q value is already going to be 0. There's a couple of other things that we can do right away, which is we know that h of 0, the initial height, is 10, and that tells us the a value is 10, which means that h of n is equal to 10. The rate, the b value, we actually already know, it told us this in the question, is 0.45, because it said that's how much it keeps after each bounce. So that becomes 0.45 to the n. And then the last part, it says estimate the number of bounces required for the bounce height to be 10% or less of the starting height. But we've actually already addressed that. So what does that mean, to be 10%? So we want to figure out how many bounces do we need for what? Well, what's 10% or less of the starting height? Well, that would be for h of n to be less than or equal to 1, because the starting height was 10 meters, so 10% of that is 1 meter. So how many bounces do I need to end up with 1 or less meters? And in this case, because we already did this table of values, to end up with 1 or less meters, well, 10 meters turned into 4.5 meters, turned into 2 meters, turned into 0.91 meters. So 2 bounces was not enough, but 3 bounces was. So that is actually our answer. So in this case, we can say from the table of values, after the third bounce. Okay, so that's what we end up with for the answer to that one. If we didn't have that in our table of values yet, we would keep trying different values, larger values, until we got one that met this criterion. Okay, and that's it for this lesson. There is some posted homework for our current textbook.